Hey, greetings, folks. You are here to get a little bit of refresher or clarification for our gas laws. So that's like Boyle's law, Charles' law, Lussac's law, and kinetic nuclear theory. So this is the review and solutions to the questions on your common formative assessment, CFA. All right. So number one, we have some unit conversions, right? So up here at the top of the paper, you should have seen our equivalencies for atmospheres, millimeters of mercury, and kilopascals. So millimeters of mercury, by the way, is often what meteorologists and weather predictors use for atmospheric pressure. So all we're going to do is we're going to express atmospheres as millimeters of mercury because pressure is often expressed in different units depending on the context. This is a useful skill. So I like to set up my measured quantity in a fraction over 1 just to help out with the dimensional analysis to know whether that goes on top or bottom. Okay, now all I'm going to do in the next step is convert that from atmospheres to millimeters of mercury. So I need to use this number, I need to use this number. So 1 atmosphere is equal to 760 millimeters of mercury. And again, you've been taught previously that the reason we put atmospheres on the bottom in this particular example is I'm trying to get rid of atmospheres and express my answers in millimeters of mercury. And since atmosphere starts on the top because it's our initial quantity, the atmosphere value has to go on bottom in that second step so that we can cancel those. And then we're left in those units. Now on my calculator, all I do is 0.37 times 760. Okay, when I do that, I'm going to get a number. But notice here that it says to round to 2 decimal places. So when I round that properly, I should get 281.20 millimeters of mercury. Okay? So the second one, I have 157 kPa. I'll do this one a little faster. Put that in a fraction over 1. I know kPa is going to go on the bottom. And I want to know my answer in ATM, so that's going to go on top. So if I go up here, I will see that 101.3 kPa is equal to 1 atmosphere. So 101.3 there, 1 there. kPa's cancel. So in this case, on my calculator, I'm going to go 157 divided by 101.3 because that's on the bottom. And when I round that appropriately, I should get 1.55 ATM. Okay. Now, you guys will notice that I'm putting units on all of my numbers. And absolutely, we need those units in the answer. So right here, units in the answer, units in the answer, every single time. We're not quite as strict about units in the setup. However, that is a good practice to be into. We're just not going to drill you too hard if you don't put them there. But absolutely, absolutely, absolutely make sure we have the correct units in our answer. And if it says to round, please round appropriately. Next one. So we have a syringe contains a fixed amount of gas. Okay? So this is a calculation problem. So I'm just going to write my combined gas law equation up here. Okay, now the reason I'm going to do this is this allows me to then go back and eliminate things that are kept constant. So this says fixed amount of gas, right? So in my equation, we need to know that is N. So N is our fixed amount. And what that means is N is not changing. So we get to eliminate N from our equation. Okay? We have an initial pressure of 0.962, so that's going to be my P1. Okay? The gas occupies a volume of 15 milliliters. So that is going to be my V1. If you push the plunger down, decreasing the volume to 5.3 milliliters, so that's going to be my V2, while keeping temperature constant. So if temperature is constant, I get to cross the temperature off, right? So what this means is I can rewrite my equation to just be P1 V1 equals P2 V2. Okay? Now I can just go ahead and substitute my values in. So for P1, I've got 0.962 ATM times V1, which is 15.0 milliliters, equals P2. That's the one I don't know yet. Doesn't tell me what that is up there. Times 5.3 milliliters. Okay? So, that is just substituting those values in where they belong. Okay, so now, if I go 0.962 times 15.0, I'm going to get 14.43. Okay, equals 5.3 times P2. So all I'm doing is I multiply those values. Get that. I'm just simplifying here. Now, all I do, you guys should have learned this some time ago in your basic pre-algebra class or algebra class. I need to find P2, so all I'm going to do is divide both sides by 5.3. 5.3's cancel there when I do that, and round to 2 decimal places. I get 2.72. Now it's a pressure, and my unit for pressure is ATM, equals P2. 2.72 ATM is my final answer. Okay, this next one, you guys are going to draw a model and do a calculation. All right, so let's take a look at this. We have 25 degrees Celsius in a rigid container. The pressure of 1.0 ATM is cooled, so the temperature is negative 50 degrees Celsius. Okay, now one of the things, red flag, is that's in Celsius. We need to make sure we get those to Kelvin. So a little note, convert to Kelvin for our calculation. But for our model, this is fine. So I'm going to go label this one 25 degrees Celsius, label this one negative 50 degrees Celsius, and then I'm just going to draw a little box. Now, this says a rigid container, which means volume is constant. So I'm going to draw both boxes the same. Okay, I'll make that little note off to the side. Or volume is constant in this case. So all we're going to show in this case is we have a rigid container, so there's no particles going in or out. So the easiest way to do this is to just draw 10 particles. Now, this is a gas, so gases spread out. 3, 4, 5, 6, 7, 8, 9, 10. To fill the space in the container, I'm going to do the same thing here. Eight, 9, 10. Okay. Now, what is different about what's going on inside this container at these different temperatures? Okay, it is the rate or the speed at which these particles are moving, and also the pressure would be different. Okay, so we can show, right, our random direction of movement for our particles with arrows. like this. Okay, so we want to show those arrows go in random directions. Now, over on this side, we are colder. We have a lower temperature. So we're going to draw the same essential thing. What we're going to do, though, is make sure our arrows are not as long. So that is our indication. These particles are moving more slowly. Okay, so what we look for here is same number of particles, same size container, just showing those particles moving at different speeds to indicate the warmer and colder conditions. Okay, now moving down to our calculation. What is the new pressure? Okay, so we have a rigid container. So we have our P1 V1 over N1 T1. So here's our combined gas law equation. Rigid container means V is constant. Now, we're not adding or taking gas out, so N is also constant. So our equation, what are we left with, is going to be P1 over T1 equals P2 over T2. When we substitute our values in, we're going to get 5.0 liters over 293 Kelvin. Okay, so again, correction there. That P1 is 1 atmosphere over our starting temperature. So remember, it says 25 Celsius. Right? So we're just going to add 273 to that to get 298 Kelvin equals P2 over a new temperature, so negative 50 degrees Celsius is going to be 223 Kelvin. Okay? Now, quick math here. We're just going to divide 1 by 298, multiply both sides by 223 Kelvin. And when we do that, we get an answer of 0.75 ATM. All right, moving ahead. We're going to move a little faster now that we've shown this basic process. So a little less talking, a little more writing. So we've got P1 V1 over N1 T1 equals P2 V2 over N2 T2. So we have chemistry student has it sealed. That means N is constant. Flexible. That means V is not constant. Container with a fixed amount of gas. Okay, at an initial temperature of 293 Kelvin. Volume of 5.0 liters. If you heat the container, causing the temperature to increase, what will happen to the volume of gas? Assuming pressure remains constant. Now we can get rid of that. So our equation is going to be V1 over T1 equals V2 over T2. So my initial volume is 5.0 liters. My initial temperature is 293 Kelvin. Going to be equal to V2, which is our unknown, over our new temperature, which is 323 Kelvin. Okay, multiply both sides by 323. And we should get, we divide 5 by 293, multiply it by 323. Okay, we should get 5.51 liters, because it's a volume. All right, moving ahead. So a weather balloon has a volume of 35.5 liters. That's V1 at standard temperature and pressure. So that's 273 Kelvin. It's T1, and pressure is 1 ATM. That is P1 Okay, after the balloon is released, it rises to where the air pressure is 0.123 atm, that's P2, has expanded to a new volume, it's V2, right? T2 is our unknown. So this is a balloon. We're not putting anything in or out. So the only thing we get to cross off this time is the amount of gas. So we're going to go P1 V1 over T1 equals P2 V2 over T2. Okay. We substitute our values in. We're going to have 1 atm times 35.5 liters over our initial temperature, which was 273 Kelvin. Okay, so just a reminder, standard temperature and pressure is 273 Kelvin when out, equals P2, which is 0.123 atm, times V2, which is 255 liters. We don't know T2. All right. So in this case, because we have so many numbers going on here, I'm going to recommend that we simplify. So we go 1 times 35.5 divided by 273. We're going to get 0.1300 on this side. It's going to be equal to 1.123 times 255 gives us 31.365 over T2. Okay? Now, a little algebra trick for you. Whenever our unknown is on the bottom or in the denominator, you can do a quick little switcheroo. Right? So I can rewrite this to be T2 equals 31.365 over 0.1300. I divide that and round. I should get 241.27 Kelvin. All right. Last, this is just a data interpretation. So it says we have a table where they're looking at different pressures, different volumes, different temperatures, just to get that relationship. Okay? N is kept constant. So we have to identify two experiments or trials whose results can be compared to show the relationship between temperature and volume at constant pressure. So all we're looking for is we're going to look at our pressure values, and we're going to look for two that match. So 120, no others are 120. 135, 135. So those two right there have a constant pressure. They have the same pressure. So that would be trial B and trial E. Okay? So what we're looking at here is for our graph, we're going to have the relationship between volume and temperature. So essentially we're looking at V1 over T1 equals V2 over T2. So temperature on the Y, on the X, volume on the Y. Now, you guys have been taught that that is a proportional relationship. If I increase temperature, I have to increase volume proportionally. That looks like that kind of graph. Adios.